Hi. Today we're going through a PAT paper in 2009 looking at question 25. So question 25 gives us a circuit of resistors, each of resistance 1 kilo ohm. And the first part asks us to find the resistance between A and B. So as always, we're going to need the formula for adding resistors in series and parallel. So we know resistor total in series is simply the sum of them all. And in parallel, the total is the sum of the reciprocals reciprocaled. If you haven't seen this already, watch our video on resistors to see where this comes from. Okay, so our first step will be to resolve this 3 here. So let's quickly draw that out. So we have a resistor here of 1, a resistor here of 1, and a resistor here of 1. Well, these two are in parallel, are in series. So we simply add them linearly according to this. So this is equivalent to a resistor of 1 here and a resistor of 2 down here, because we simply add these two together to get 2. Well, then we have to add these two in parallel. So this is equivalent to 1 resistor, and its resistance is going to be, well, 1 over 1 plus 1 over 2 to the minus 1. So that's 1 plus half is 3 over 2, to the minus 1 is 2/3. Okay, so now we have that this is equivalent to 2/3 of a kilo ohm. Okay, so let's remove this. So now we can rewrite the whole, we can redraw the whole circuit with A here, and up here we have our resistor of 1 kilo ohm at the top, and then B. And then down here we have the 1 again, but now we have a resistor of 2/3, which is the resolved resistor of these 3. Okay, then we simply add these two in parallel, in series, sorry. So that is equivalent to a resistor of 1, and a resistor of 1 plus 2/3, 5/3, and then B. And now we simply add these in parallel. So you have A, and then some resistor, and B. So what is this resistance? Well, again, we add in parallel, so it's 1 over 1 plus 1 over 5/3, 3/5, to the minus 1. Well, 1 plus 3/5 is 8/5, and 8/5 to the minus 1 is 5/8. So that is 5/8 of a kilo ohm, which gives us a total resistance between A and B. Okay, so in the second part of the question, we're told that a battery of 6 volts with internal resistance 125 ohms is connected across A and B. And we're asked what current flows between these terminals C and D. Okay, so let's draw this on. So what that means is we have a battery up here with an internal resistance of 125 ohms, and this is 6 volts across the terminals of A and B. Now, a better way to visualize this might be that it's basically a battery and a resistor in series with the resolved resistance of this. So what I mean by that is that this is equivalent to, well, here's our battery, here's its internal resistance, and then here's our resolved resistor down here, where A was here and B was here. So just to clarify, this is the resolved resistance of this weird parallel series combination. Okay, so doing that, we can now use our potential divider method to find the potential difference across this resistor. So the resistance, the voltage from A to B, will be equal to the fraction it is of the total. So that's 625 out of the total, which is 625 plus 125 times the voltage. Well, that's equal to 625 out of 750 times 5, which is equal to 5 volts. So the voltage across AB, across these 2 points, is 5 volts. Well, we had this here as our resolved resistance of these 2 bottom components. Sorry, of these 3 components being 1 resistor here, this resistor here, and the resistor on top. And if we label onto this, that we had, in fact, CD would be within this resistance here. So what we're going to think about now is that across the ends of this resistor network, we have a voltage of 5 volts. Now, this branch here is in parallel with this branch here. And as we know, parallel circuits divide voltage. Sorry, have equal voltages across their branches. So that means there's a voltage of 5 volts across here and a voltage of 5 volts across here. Okay, so that means we can now ignore the top. So we're now considering only this bottom part, which we know is 5 volts across it. So now what we can do is we can think, well, what voltage is going to be across this section? Because this here is equivalent to this down here. So we have 5 volts across these two ends. And we want to find what fraction of the voltage does this section here get. Okay, so what would that be? Well, let's write that down. So it would be, in fact, let's label it. So let's label this resistor as E and this as F. Okay, so what's the voltage across F going to be? So the voltage across F will be the voltage across this network here, this small 3 network. So voltage of F, VF, will be equal to its fraction, so that's 2/3 out of the total, 1 plus 2/3 times V. Well, that's equal to 2/3 over 5/3 times 5. And that's equal to 2/5 times 5, or 2 volts. So the voltage from across these terminals here is 2 volts. And again, we have that this is a parallel network. So you have this actually 2 volts across here and 2 volts across here. So now we just simply have to consider what current runs through this branch. So we know current is the same in everywhere in a series branch. So we define what current runs along here. Well, we know it has a voltage of 2 volts across here, and we know it has a resistor of 1 plus 2 kilo ohms. We know V is equal to IR, and therefore I is equal to V over R. So now we simply sub in. So the current across C and D is the voltage, 2 volts, over the resistance, 1 plus 1 times 10 to the 3, which gives you an answer of 1 milliamp.